Hey guys, welcome back. So, this is our last part of the entropy lecture. We're going to be doing the in-class problems to make sure that we've got some grasp on what we've been talking about. Okay, so here are some questions that potentially you might see. So, isn't it nice when I give myself instructions? So, I want you to tell me what you would predict the sign of delta S to be for these processes. Okay. So, would you expect it to be spontaneous or not spontaneous? And this should be okay. So in this first one, we're going to be going from KNO3 to KClO3 to 2 KCl solid plus 3 O2 gas. So one of the rules that I have for looking at how spontaneous something is going to be is the change in the number of moles of gas. So I'm going from no moles of gas to 3 moles of gas. That would be favorable. So I would expect that to be an increase in delta S. It's positive. So positive, again, is going to be favorable for delta S. Okay. When we talk about going from H2O liquid to H2O gas, again, we're increasing the number of moles of gas, so I would expect that to be a positive delta S. When we talk about going from 4 moles to 2 moles, we talked about this. 4 moles to 2 moles is going to be a negative delta S. We actually calculated that value a couple of slides ago. But that is going to be a negative value for that. We talk about NaCl solid going to Na plus aqueous plus Cl plus aqueous. We've gone from 1 mole of stuff to 2 moles of stuff. Okay. Now, granted, we've also gone from solid into the liquid phase. So both of those are favorable things. So that's a positive delta S. When we talk about going from KCl solid to KCl liquid, we're going from high order to less order. So that's going to be a positive delta S. When we talk about going from CO2 solid to CO2 gas, that's also going to be a positive delta S. When we talk about going from H plus C2H3O2 minus, going back to HC2H3O2, we're going from 2 particles to 1 particle. 2 to 1, that's going to be a negative. When we talk about carbon plus O2 going to CO2, we've now gone 1, 1 in terms of gases. Okay, so there's nothing favorable in that. We've also gone from 2 particles to 1 particle, so that's not overly positive. I would expect this to be negative delta S, but a fairly small one. When we talk about H2 gas, Cl2 gas going to 2HCl, again, we're looking at not much in terms of gas, number of moles of gas change, but we are looking at a change in terms of where we are. So H2 and Cl2 going to the more complex HCl. So I would expect that to be positive delta S, but again, small. Ag plus Cl plus or Cl minus aqueous, both of those aqueous going to AgL solid. We've gone from the aqueous phase in the liquid to the solid phase. I would expect that to be negative delta S. We have lost entropy in doing that. 2 N2O5 goes to 4 NO2 plus O2. We're going from 2 moles of gas to 5 moles of gas. That is a favorable process, so that would be a positive delta S. Okay. 2Al solid plus 3I2 solid goes to 2AlI3 solid. So we've gone from 5 particles to 2 particles. So even though there's more entropy in it because it's a bigger, more complex molecule, we've still gone from 5 to 2. I would expect that to be a negative delta S. I think that's probably going to be the biggest factor there. H plus aqueous plus OH minus aqueous going to H2O liquid. Yeah, no, we're still taking two things and making one out of them, so that's going to be a negative delta S. Wouldn't expect it to be a huge value, but it should be negative. 2 NO gas going to N2 plus O2. So no net change in number of moles of molecules. We're going from a more complex to a simpler one. I would expect that to be negative delta S. And then H2O gas to H2O liquid, going from gas to liquid, that is going to be more order, so that's going to be a negative delta S. Now, you should be able to find a table of delta H values or delta S values, and I don't remember if I have put one on D2L or not. Let me make myself a note. And when we do that, we should be able to calculate values for each of these, as well as predicting their sign. So if I look at my internet, I look at my teaching tools, standard thermodynamic values. This is the table that I intend to make available to you. And what you'll see in this table is that there are delta H values, the enthalpy, the entropy, and then something that we haven't talked about yet, which is the Gibbs free energy. We'll talk about that in the next lecture. Okay. That means there we go. So what you'll see is that this is in order. If you go down to KCl03, use my Control F to find this. KCl03 should allow me to search within this document. Like I'm searching for that. I see 1 of 1. It's right there. That means that my enthalpy is the first one and my entropy is the second one. 142.96728. So my 2 KClO3 solid, and that is a solid. So this value 142.96728, that gives me 2 KCl gas plus 3O2 gas. And if I look at my KCl gas, that's 239.49216. I'm taking all of those decimal places because they've been provided to me, so I might as well use them. And then the O2 should be not 0. Actually, and O2 gas. My entropy is 205.205. 205.02852. And so if I were to look at my delta S, that's equal to the sum of the stoichiometry products minus the sum of the stoichiometry of the reactants. And so my products, I'm going to have 3 times that 205.0285552 plus 2 times the 239.49216 minus 2 times 142.96728, and that's going to be equal to 3 times 205.02852 plus 2 times 239.49216 216. And then I'm going to subtract 2 times 142.96728. And it gives me 808. 135,416. And that's a happy value, right? And I know that that's in joules per mole Kelvin. And I'm going to leave it in joules per mole Kelvin because I didn't make a single mole. I made 2 moles. So that's going to be something that we need to pay attention to. So I'm going to leave that in joules per mole Kelvin. Now you should be able to calculate values for the rest of these. So I'm going to walk through a couple more. Let's go for our H2O. So H2O gas is 188.715136. So H2O, and my equation says liquid, to H2O gas. My gas, again, is 188.715.136. And my H2O liquid is listed as 69.91464. And so if I were to do products minus reactants, again, 188.70736 minus 69.91464, because I have 1 mole each. That gives me 118.79272. Okay, so again, just like we talked about before, products minus reactants, remember to multiply by the stoichiometry. So that's the kind of thing that we're going to see there. I will put the numerical values for the rest of these on D2L, and I will put them down here next to what we expected our sign to be. So this is 808.135416, and these are in joules per mole Kelvin. And my second one is 118.79272. And I will put the rest of them on D2L, those actual values, okay? I'm expecting that that's not going to be that bad because we've done this before. So as long as you have this table, you should be fine. And I will make sure that I put this table up for you on D2L so that you can use this. This will be useful in terms of calculating enthalpies, entropies, and free energy when we get to free energy, okay? Okay, awesome. We should be able to handle that. Now, for which reaction do you expect the change in entropy to be negative? Okay, so I've got a couple of choices here. I want to know when is it going to be negative, i.e. not favorable. So I go from 2 solid, 1 mole of O2 to 2 moles of O2. I would expect this to be favorable. I would expect that to be a positive delta S. Solid to liquid, I would expect that to be a positive delta S. H2O liquid at 25 degrees goes to H2O liquid at 50 degrees. Higher temperature, more disorder, I would expect that to be a positive delta S. So Cl2 plus 2HI goes to I2 solid plus HCl gas. Okay, we've gone from 3 moles of gas to 1 mole of gas. We've also gone from all gas to 1 solid and 1 mole of gas. I would expect this to be negative. And so that would be the answer that I'm looking for. Okay, so there's that one. Which has the greatest absolute entropy? So which has the most disorder? That's what we're being asked. And we're all at 25 degrees. This should be a liquid. So 1 mole of C solid. It's a solid. CH2Cl, C2H6, and this is a liquid, this is a liquid. I see 1, C2H6, that's a gas. I would expect this one to have the greatest amount of disorder because 1 It's a gas at 25 degrees, so it has the most disorder based on its phase. The other thing is that it's a fairly big molecule. C2H6 is fairly complicated, so I would expect that to have more disorder than C solid or CH3Cl. Okay, so that would be the one that I would choose. Which of the following represents an increase in entropy? So increase in entropy, more favorable. So freezing water, no, because that's less disorder. So that's a negative delta S. Boiling of water is a positive delta S, going from liquid to gas. Okay. Crystallization of salt from a supersaturated solution. So we've gone from high entropy to low entropy. So we've crashed out that solid from a liquid, from being in the aqueous phase. I would expect that to be a negative delta S. The reaction of 2NO to give me N2O2, I would expect that to be negative because we're going from 2 moles of gas to 1 mole of gas. The reaction of 2H2 plus O2 to give me 2H2O. So we go from 3 moles of gas to 2 moles of gas. I would expect that to be negative as well. And so again, we only have one where we would expect our entropy to be going up, and that's boiling of water to the gas phase. Okay, so that's awesome. Let's look at 19. For which of these processes would delta S be expected to be most positive? Okay, so most favorable. So going from O2 plus 2H2 to 2H2O is not great. That's going to be negative delta S. Again, I would expect that to be negative. Liquid to solid is not favorable, so I would say that's negative delta S. N2O4 to NO2, well, that's going to be okay, because we're going from 1 mole to 2 moles gas. NH4NO2 solid going to N2 plus 2H2 gas. So we've gone from 1 mole of solid to 3 moles of gas. I would expect this to be the most positive. Okay. So even though the one before it was also favorable, that's the one that I would expect to be the most favorable. Which of the following reactions do you expect to have a decrease in entropy? Decrease in entropy, not favorable. So solid to liquid is positive. That's a good thing. Fe solid plus S solid goes to FeS solid. So we're going from 2 to 1. Not great. Not great. I would say that's probably negative. 2 Fe solid plus 3 halves of an O2 gas goes to Fe2O3 solid. I would again expect that to be a negative. And ranking the two, I would expect this one to be the bigger. HF liquid to HF gas, this is definitely going to be a positive delta S. And 2H2O liquid going to 2H2O liquid plus O2 gas, that's definitely going to be positive as well. And I would say out of the two that we have that we expect to be negative, this would be the one that's the most negative. Okay, because we're going from a solid and a gas to one solid rather than 2 solids to 1 solid. So I would expect that to be a bigger change. Okay, awesome. We got anything else? Yes, I believe that we do. I think we have a couple over here. Yes. Under which set of conditions is a chemical reaction most likely to be spontaneous? Well, okay. So let's talk about this for a second. So we're talking about delta H, and we're talking about delta S. And we said that a change in delta S that's positive is good. Negative delta S is bad. Delta H being negative is good. Being positive is bad. Okay. So I can look at this and I can say, all right, fine. Positive delta H. I wouldn't expect any of those to be particularly spontaneous. So I'm going to eliminate both of those for now on the basis of the delta H. If I look at the other two, the delta S's that are present, positive delta S is the one that I want. Negative is the one that I don't want. So I would expect that this one would be the most favorable, because that has conditions for delta H and delta S that I want. Okay, so that's how I would choose them. For the process O2 goes to 2O gas with a delta H of plus 498 kilojoules. What would be the predicted sign of the delta S and the conditions under which this reaction would be spontaneous? Okay. So just based on our entropy, we're talking about positive delta S being good. Okay. So positive delta S. So I'm going to look at these two and say, nope, based on what I know right now, I don't like those. So positive. And of course, I need to take in energy. That delta H is positive. So if my delta H is positive, I need to take in energy to get it to happen. So the higher the temperature is, the more likely I am to have the energy that is required to make that happen. So that's why I chose the one that I chose. Okay? So hopefully that makes sense to you. Some of the things that we've done there are intuitive or will become intuitive. That's what we're looking for. So that's what we've got for in-class questions. If you have any questions, comments, problems about this, let me know. I will get this uploaded to D2L so that you can practice with it. And I think that's everything I've got for this lecture. So that takes us through entropy. Awesome. I will talk to you guys soon. Thanks.